And welcome to the next instalment of the Monash Centre for Astrophysics Public Talks. This is probably the last one for this semester, but keep an eye on your email, and if you want to get on the email list, we'll have an email list here afterwards so you can sign up. Tonight we're very pleased to have Professor Tim Bedding speaking. Tim is a world expert in astroseismology, which is the study of stellar oscillations or vibrations, and he'll explain what that means shortly. After earning his PhD at the University of Sydney, Tim moved to Germany to work as a postdoctoral researcher. A few years later, he got a job at back at University of Sydney to take up a lecturing position, and he's now a full professor and also the head of physics at University of Sydney. He's also a great teacher and speaker and has been awarded the University of Sydney's Excellence in Teaching Award. He almost literally jumped at the opportunity to give this talk tonight when I asked him, as much as you can jump in email. He leads a research group at Sydney University that's involved in several international projects, including a worldwide network of telescopes, which is studying oscillating stars, as well as NASA's Kepler Mission. And that's what I'll tell you all about tonight, planets and stars. Please welcome Professor Tim Bedding.
Thank you, Simon. So good evening, everyone. How's the sound up the back? Is that okay? Good. All right, well, thank you for coming along. I really do appreciate it. It's always lovely to come to Melbourne and enjoy some beautiful weather. It's raining in Sydney today. I had a great day here with the group who are doing a lot of wonderful astrophysics research. And what I'd like to do this evening is tell you a little bit about some of the research that we've been doing in collaboration with people around the world. So there's two parts of this talk, and they both involve this beautiful space telescope called Kepler. How many people here have heard of Kepler before? Excellent. So Kepler is a wonderful space mission. It nearly died, but it's back again, and it's back observing, thanks to some wonderful, clever techniques from the NASA people. So this talk is in two parts. The first part is about planets, because the main aim of Kepler is to find planets around other stars, as you probably know if you know anything about Kepler. So that's the planets part. But the second part of the talk is about what we call Starquakes, or more formally, oscillations in stars. And that's the research that we mostly do. And so I'm going to divide the talk into two parts, and about halfway through I'll stop, and if you want to ask any questions, I'd be very happy to try to answer them. So I should tell you that the first part, the planets part, is not the part that I directly research on. And so the second part of the talk is the part that we are doing most of our research on, but we do a little bit of both. So let's start at the very beginning, just to make sure everyone is on the same page. We live on a planet in a solar system, which used to have 9 planets in it, but as you probably know, a few years ago, one of them unfortunately got demoted, poor old Pluto. But never mind, because there's a spacecraft on its way to Pluto that's arriving in a few months. So stand by for that. That's going to be very exciting. The first time a spacecraft has gone up close to the Pluto system. And Pluto has, in fact, its own little moons. The point of showing you this slide is to show the sizes. Now, this is not to scale in terms of distance. The planets are a lot further away from the Sun than this, but the sizes are right. So the Sun is huge compared to all the planets, even Jupiter, which is the biggest of them. And so if you're trying to find planets around other stars, it's really difficult because you're looking for a tiny planet in comparison to a large and extremely bright star. And so that's the challenge. How do you find a planet around other stars? And up until maybe 20 years ago, about the time I moved to Germany, in fact, as Simon mentioned, the number of planets known around other stars was 0. And in the last 20 years, that number has skyrocketed to now many, many thousands. Now to the point where we're quite confident in saying that most stars in our galaxy actually have planets around them. That's an extraordinary breakthrough. Now, someone always asks me, is there life on any of those planets? So let me tell you straight up, we have no idea. Right? There's no really way of knowing, but at least we know that there are a lot of planets out there. So, the solar system is big, and most of it is empty space. So this is now to scale, showing the orbits of the planets. And you can see immediately, by the way, that poor old Pluto is the odd one out. It really isn't like all the others. It doesn't orbit in the same plane, and that's one of the reasons why it was kicked off the list of planets. But all the other planets orbit nicely in a plane, more or less. And the further you are from the Sun, the longer you take to go round. So the Earth, of course, takes a year to go around the Sun. But if you head out to the outer reaches of the solar system, like, for example, where Jupiter is here, it takes about 12 years to go around the Sun. And Neptune takes, can't remember, nearly 200 years, I think. Does anyone know? I'm not very good with remembering numbers. So the further you are away from the star, the longer it takes to go round, because the gravity is weaker and you've got further to go. Okay? So if you want to find planets around other stars, the best place to look is in close. You don't have to be as patient. You don't have to wait so long. And indeed, the planets that have been found around other stars, at least initially, were all fairly close in. So there are a lot of stars in the sky. This is a picture of the sky. It's seen from the southern hemisphere. Do you recognise it? It's hard because there are so many stars. If you live in a city, you don't see this many stars. Just to guide your eye a little bit, let me put some lines on there. That's the Southern Cross. Okay? The stars on our flag. These two stars down here are the two pointers, Alpha Centauri, which is the closest system to our own sun, Beta Centauri and the Southern Cross. So every one of these little dots is a star. Many of these may have planets around them, but how do we find out? It's very difficult. But there are a lot of stars. In our galaxy, which looks a bit like this is obviously not our galaxy because we're inside it, but it's a bit like our galaxy, about 200 billion stars in our galaxy alone, and more than 100 billion galaxies in the whole universe. So if you're asking the question, how common is life out there, how common are planets, there's an awful lot of stars to look around. Now, the stars are quite different. They're not all like our sun. Some are a lot bigger and brighter. Most of them are actually smaller and fainter. Our sun is kind of average. So we want to find planets around these stars. How do we do it? The problem, as I've already said, is that compared to their host stars, the planets themselves are very faint and difficult to see, caught in the glare of this enormously bright star. So there's a few ways that you can address this problem, but the way that Kepler addressed this problem is using this method. Does anyone know what's happening in this figure? Yeah? It's a transit of Venus. It's the transit of Venus that happened in 2004. There was another one a few years later. If you missed it, bad luck, because there won't be another one in our lifetime. They come in pairs a long way apart. Captain Cook discovered Australia shortly after observing a transit of Venus in Tahiti. So this is obviously sped up. The whole thing took a few hours. Imagine you're observing from a distance. So not where we are on Earth, but observing the sun from a long way away. Can you see that for those few hours, the sun would have got a little bit fainter? Not by much, because Venus is not covering very much of the sun. But if the planet were bigger, you would have had more of it covered. So if you're observing the sun on this day from a distance, you would have seen the sun get fainter for a few hours. That's called the transit method of finding planets, and it's the method that Kepler uses. Now, you might ask yourself, why are transits of Venus so rare? Venus goes around the sun faster than the Earth does. It takes less than a year. Why don't we see a transit of Venus every year or less? Does anyone know the answer to that? We have to be in the right place, exactly. And the Earth's orbit and Venus's orbit are slightly tilted with respect to each other. And the Earth is moving too. So it's like being on a moving platform. And so from the Earth's point of view, transits of Venus don't happen all the time. It's the same reason that we don't get an eclipse of the sun every month, because everything's not lined up. But if you were observing the sun from a very long way away, that wouldn't be an issue. And every time Venus went around the sun, it would either transit if you happen to be in line, or most likely it wouldn't, because you might be looking from the wrong angle. Do you see my point? So if you're looking for a transiting planet like Venus or the Earth, you do expect it to happen regularly. But it's not very big. The amount of light that's blocked by Venus there is very, very small. Okay, it's only a part in about 100,000 or something like, even less. So you need very accurate measurements. Just for fun, here are some gratuitous pictures of the transit of Venus, just because I found them on the web and they're pretty. The Sydney Harbour Bridge on the top. And this is the International Space Station, I think, going across the sun's disk as well. So if you're observing the star from a distance and measured its brightness, during a transit, you would see the bottom graph. It's a graph of the brightness of the star versus time. And imagine it takes, in this case, a few hours. Then nothing happens for another year or so, and then it happens again. Then nothing happens for another year or so, then it happens again. You have to be incredibly patient to do this. You also have to be lucky, because if you were looking at the wrong angle, you wouldn't see it. The next animation is a bit similar. It's showing a planet going around a star. And here you can see that we're nearly edge on. And so we do see a transit. There it went. The planet, of course, goes around the back. And remember, this is exaggerated. The planet is probably a lot smaller than that. and it's not going nearly that fast either. But you can see the principle of it. You can also see some of the things that might make things hard. Can you see the little black spots that are going around on that star? They're like sunspots. They're dark patches. And the sun has those, and so do other stars. So that's one of the things that might confuse you if you're looking for stars getting a little bit dimmer. So the graph I showed you on the previous slide here looks perfect. It's completely flat except where it dips. But in real life, it's not so simple. But nevertheless, the method does work. And NASA's Kepler mission, which was launched in 2009, was dedicated to this one aim of staring for years at thousands, hundreds of thousands of stars, waiting patiently, hoping that some of them would show this effect. So here are just a few pictures of the telescope before launch. It's not as big as the Hubble Space Telescope, which is huge, but it is still pretty big. It's one of the biggest space telescopes ever launched. It wasn't cheap, I can assure you. But it was paid for by NASA. The purpose of the mission was dedicated to finding planets around other stars. So it was launched in 2009 from a Delta rocket. And at its focus was this beautiful array of detectors. They're CCD detectors, silicon chips, similar to the ones that are in your mobile phone, only a little bit bigger and more expensive. And that area is looking at all these stars and measuring their brightnesses. Every half hour, measuring their brightnesses over and over and over again. Now, why would you launch a telescope into space to do that? Well, the main reason is the Earth's atmosphere. So if you go out at night and see stars, you see them twinkling. It's very pretty. But that twinkling isn't real. Well, I mean, it's real, but it's not the stars. It's the Earth's atmosphere. The shimmering effect. It's like looking from the bottom of a swimming pool through the Earth's atmosphere. That makes it impossible to measure the brightness accurately enough to do what we want to do. So you launch the telescope into space. You get it above the atmosphere, above the weather. It can observe continuously. And that's what it did. So where did it look? It looked at a patch of sky in the northern hemisphere, near the Milky Way in the north, in the constellation of Cygnus, the Swan. They chose that region of the sky because it was close to the plane of our galaxy. So this very bright patch of stars, the Milky Way, is the plane of our galaxy, which is disc-shaped. They didn't choose this region here because there are too many stars. You want a lot, but not too many, otherwise it's too crowded. So they chose a region up here, a little bit away from the plane of the Milky Way, and they just stared at it and stared at it over and over again, measuring brightnesses of every star every half hour for years. Very boring mission. This is a slide that shows you, in fact, what a tiny fraction of our galaxy they're actually looking at. So the top picture is a sketch of our galaxy. The sun is here, and the sun goes around our galaxy in this very big orbit. And the region that Kepler is looking at is this kind of yellow bit here, which is blown up here. So it's only really in our local neighbourhood. The galaxy is enormous. But still, even in that local neighbourhood, there are hundreds of thousands of stars to look at. And some of them will have planets, and some of those planets will be in the right orientation, just edge on, that we'll see the transit. Now, you may have heard that Kepler died because a year and a half ago, the reaction wheels that steer the spacecraft broke. There are 4 of them. You only need 3, but 2 of them are broken. There are 2 left. The 2 that are left are fine, and they're going to keep working as far as they can tell. What do those wheels do? Well, they spin, and by adjusting the rate of spin, they can steer the spacecraft. Because when you're in space and you want to point the telescope very accurately, you can use thrusters to do it, but that's a bit crude. So a more precise way of doing it is to have a wheel that's spinning. And if you want to turn to the right, you spin the wheel up a little bit to the left. Okay, so it's a little bit like if you sit on a revolving stool with a bicycle wheel that's spinning, and you spin it a bit faster, you'll turn the other way. It's called conservation of angular momentum. Very clever technique. Unfortunately, 2 of the reaction wheels on the spacecraft were a bad batch. They lasted for 4 years, but then they stopped working. But fortunately, they figured out a way of continuing to use the spacecraft in a different mode with 2 wheels plus the thrusters, and it's continuing to operate now. And it's still taking data, but not of the field that I showed you in Cygnus, of different parts of the sky, for reasons that are slightly complicated, but I can explain them later if you're interested. Anyway, here is what the sky looks like when you observe it with Kepler. This is not the sort of thing you see. It's not the sort of picture that you put on one of these beautiful slides here with lots of pictures of galaxies and things. Just a whole lot of little dots. Every one of those little dots, most of which you can't see, are stars. Let's zoom in a bit so you can see a little bit better. Just the 2 of the detectors. Still lots and lots of dots. You measure the brightnesses of every one of them every half hour for 4 years. And this is the sort of thing you see. So this is a discovered planet. It's a graph of the brightness of one of those stars, no idea which one, over about a month. And most of the time it's got the same brightness, but every so often, every 3 or 4 days, it dips downwards. You see that? And that downwards dip is about 1%, goes down to about 0.99. So about 1% of that star is being covered by a planet that's going around very regularly. Now the reason that it goes down and up, and you can see kind of holes there, is because it's only measuring every half hour. And remember, it only takes a few hours to transit. So depending on when you happen to observe it, it might be on the way down or on the way up. But what you can do is divide that data set up into equal parts and then put them all on top of each other and have a closer look. And that's what this is. So this is all of the data phased up with exactly the right period, and now you can see that beautiful dip. So that's a beautiful planet. It's the type of planet we call a hot Jupiter because it's very close in. It's going around its star only in a few days. Right? In our solar system, the fastest planet is Mercury, and that takes 3 months to go around the sun. One of the amazing discoveries in the last 2 decades has been there are a lot of planets out there much closer to their star than ours are. It's called a hot Jupiter because this is a big planet. 1% of the area, that's a big planet. That's a Jupiter-sized planet in a close-in orbit. So it would not be a pleasant place to live, although it could have moons on it. You know, like in Star Wars with the moons of, what's the one where the Ewoks were called? What? Endor, yeah, that was a moon. Anyway, we have no evidence yet for moons around planets. But this is the sort of thing that Kepler finds. You might also wonder why it goes down sloping. You see how it goes down sloping and not vertically, the brightness. That's because stars are not uniform in brightness. When they go across a star, the star's brightest in the middle, but it's less bright at the edges. And so that's why you have this U shape here at the bottom. So that's an example. Here are a bunch more of hot Jupiters and hot Neptune-sized planets with very short orbits. Now, these were the first to be found. Why? Because they're the shortest period. You only need a few weeks of data to see these ones. Right? Imagine being on these planets. You get a birthday every 3 or 4 days. Right? A lot of presents. You can tell how big the planet is by how big the dip is. So this is a bigger planet with a big dip. This one over here on the left is a very small planet with a very small dip. You see that? So the size of the dip tells you how big the planet is. The top pictures are not real, right? They're just artist's impressions. The real data is this one, the graphs in the middle. So from that, as I said, you can infer the sizes of those planets. And so the planets that I just showed you look like this. Most of them are, in fact, slightly bigger than Jupiter, but the one on the left, which is now on the right, is smaller. The colours are not real. Artist impression. We have no idea what the colours of the planets are, although there are techniques for inferring what planets are made of, which we can talk about a little bit later if we get time. All of them are a lot bigger than the Earth. So at this point, we're a long way from finding Earth-sized planets, but this was one of the first results that Kepler produced. As I said before, they're called hot Jupiters because they're Jupiter-sized or bigger, most of them, and they live very close to their stars. And so here are some beautiful artist impressions of what it might look like to be in such a solar system. So here's a graph. It's now actually a bit out of date, but it shows the main features. It shows all of the planets that have been found by Kepler. And every one of these spots is a planet. And the horizontal axis is the period of the orbit in days, how long it takes to go around its star. So the ones we've just been looking at only took a few days, so they're on the left. So they're these ones right on the left here. The Earth takes a year, 365 days, so the Earth is over here. The vertical axis is how big the planets are in units of the Earth. So the Earth itself would be a spot at 365 days over here. Neptune is a lot bigger than the Earth, but it also has a longer period, so it would be more out to the right. Jupiter is even bigger still. So as you can see, most of the planets that have been found by Kepler are in fact somewhere between Earth and Neptune in size. So the ones I showed you at the beginning, the hot Jupiters, are in the top left corner. They were the easiest to discover. The colour, by the way, tells you when they were found in the year 2010, 11, 12 and 13. And as years have gone by, more dots have appeared. And what you can see is that the yellow dots, the more recent dots, are the smaller planets because they're the hardest to find. You need more accurate data. And also the longer period planets are harder to find. You have to observe longer for them. Every one of those dots is a planet around another star. Extraordinary. Absolutely amazing. Here's another graph. The difference with this graph is the horizontal axis is different. So the vertical axis is the same. It's still the size of the planet, the Earth, Neptune, Jupiter. The horizontal axis is now an estimate of how hot the planet is based on how far it is from its star. Why do we care? Because we're interested in finding planets that might be like ours, that might be cool enough to have liquid water and life and little green men and women and whatever, okay? And so how hot do you want it to be? Not too hot, not thousands of degrees. Kelvin, by the way, is a bit like Celsius. Think of them as the same thing. So we want the planet to be, well, not quite the same thing. We don't want it to be thousands. The temperature in this room is about 300 Kelvin at the moment. And so we want them to be in that green band there. Some people call that the Goldilocks zone, the zone where it's not too hot, not too cold, just right. And as you can see, at least some of the planets are in that zone. A lot of them are a lot hotter because they're closer to their parent stars. So as you can see, there's a lot of information on this graph. The next graph shows you the distribution of the sizes. And there's nothing new on here. It's more or less confirming what I already said. Most of the planets that have been found are sort of the size of Neptune. There are a lot that are in between. They call them super-Earths, somewhat in between. And quite a few that are as small as the Earth or even smaller, but also a whole bunch that are big as Jupiter and bigger. So the main takeaway message from these last three graphs is how varied the galaxy is. You start with one solar system, ours, which has a Jupiter in a 12-year orbit. Nothing in an orbit shorter than a few months. What you find is a whole bunch of planets that have sizes similar to Neptune, very few Jupiter ones comparatively, and a whole bunch of planets that are much closer in to their stars than we are. So solar systems are common, but also many of them are very different from our own. So this is one of the graphs that I think most people are most excited about. It's asking what fraction of stars have at least one planet around them. Now remember the orientation, you have to correct for that. So we don't see every planet with Kepler because you have to be lucky to see it. It has to be edge on. So most of the stars in Kepler, even if they have planets, we don't see a dip. But we can extrapolate. We can do the correction for that because we know, assuming that the orbits are oriented randomly in space, we know that if we see a certain number of stars with planets, then there must be a whole bunch more that aren't edge on. Do you follow me? So once you've made that correction, these numbers here tell you the fraction of stars that have at least one planet. And as you can see, about 15% of stars have a planet about the size of the Earth. About 20% have a super-Earth. About another 20% have a mini Neptune. And a fairly small number have gas giants like Jupiter and Neptune. But still, these numbers are pretty impressive. 10-15% of stars have planets. Remember, there are hundreds of billions of stars in our galaxy, which means that there are tens of billions of planets, maybe more. There are an awful lot of planets out there. Remember, 20 years ago, when I first went to Germany, the number of planets on this graph was 0. It's incredibly rapid growth. I should point out that not every planet was discovered by Kepler. This talk is about Kepler, and it's a wonderful mission. A lot of planets were discovered using other methods, some from the ground, a lot by astronomers in Australia using Australian telescopes, for example. So there are other ways of finding planets. I know this is a somewhat biased version, but given the limited time, I only have a limited amount I can talk about. So I want to talk now about a couple of special ones. This one made the front cover of Nature, which is Science's version of Playboy, I guess. It's the kind of... Does Playboy even still exist anymore? Anyway, it's the Science's thing to get published in. It's the most exciting journal, and to make the front cover is pretty exciting. And this was one star with 6 planets. So in other words, when you watch the light from this star, it dips from 6 different planets, all going around the same star in the same plane, but with different periods. Amazing. One solar system. Completely unexpected result. I mean, our solar system has 8 planets, but they're not aligned well enough that you would see them all transit. If you're in a spot to see the Earth transit, you wouldn't see Venus transit because all the orbits are slightly tilted. This is a system where they're almost exactly flat. So here's just an artist's impression of what it might look like close up. Because we don't have pretty pictures to show, we have to rely on artists to make pretty pictures. Here's what the system actually looks like. So on the bottom is our solar system, Mercury and Venus, the inner part. All of these 6 planets fit in this region. So apart from one, they're all closer to their star than Mercury is to ours. So they're only going around in days and weeks and months. It's a very compact solar system. And here's another one, Kepler 16. This is a circumbinary planet. What does that mean? Well, a binary star system is 2 stars. Our sun is on its own, right? There's just one star in our system. But many of the stars in the sky, in fact about half of them, have friends. They actually have pairs of stars going around each other. So 2 stars in a system. And this is an example where there's 2 stars in a system quite close, and around them is a planet. So if you lived on that planet, you're going around 2 stars. You would have 2 suns. And a photograph taken on that planet would look a little bit like this. So for obvious reasons, these are called Tatooine systems. This is, of course, where Luke Skywalker grew up, the planet of Tatooine, which, of course, was photoshopped, or probably not photoshopped in the 70s, but however they did it back then, into having 2 stars in its sky. Okay, so I'm going to pause there because I'm halfway through, and it's exactly 6:30, so that was good timing. I'm going to give myself a bit of a rest and ask if anyone here has any questions. We do have a microphone because this is being recorded. Apparently we're all going to be on YouTube, so I hope you all, actually no camera, so we won't get to see you or me, but you'll get to hear yourselves on YouTube. So James has a microphone. Does anyone have any questions you'd like to ask?
Yes, sir. Thank you very much, and welcome to Melbourne. And hope you brought some of that lovely weather to us here that we're currently experiencing. My question concerns, we used to consider the orbital period of Mercury fast, and we have planets now with periods of 4 days and less. How do you account for the evolution of such systems? How could this possibly have happened?
That's an extremely good question. How did a system form with planets that close, and how did they survive? The answer is that it turns out that a planet, even a planet like Jupiter, can survive close to a star, provided it's massive enough to hold itself together, even though it gets very hot. So the first thing you have to understand, how did the solar system form in the first place? It's not completely clear, but basically there was a whole lot of material that formed the sun in the middle, and as it was rotating, some of that material formed a disk around the sun, and the gravity inside that disk formed clumps, which got bigger and bigger, and some of them became big enough to become planets. I've glossed over an entire subject there. It's very complicated, but so that's the idea. So the question then is, where do planets form? Do they form further out, or do they form close in? And the answer seems to be they form everywhere. In our solar system, for some reason, there are no planets in the middle. And you might have asked the question the other way around. You might have said, why is our solar system unusual in not having planets near the middle? Right? The answer seems to be that there are some systems which have planets close in and some that don't. I guess that's the short answer to your question. The longer answer is that it's work in progress, and theoreticians who model these sorts of things are working on it.
Thank you.
Hi. You gave some figures on the estimated temperature of the planets. I was just wondering, does that estimate come from the period of the dip, or is there some other means also of estimating the temperature of the planets?
That's a good question. So it comes from how long, the period of the dip, so how long it takes the planet to go around its star. That tells you its year, but you also need to know how bright the star is, because stars are all very different. And so that's actually where the second half of my talk comes in, and I'm going to tell you in a minute how you can tell how big stars are and how bright they are. But the bottom line is that if you're close to a weak star, a wimpy star, then you might have about the same temperature as if you're further away from a bigger, brighter star. So the stars that are in the Goldilocks zones, the planets in the Goldilocks zones, the green, might be where we are, in other words, 150 million kilometres from a star like ours, but they could be a lot closer. In fact, most of them are a lot closer to fainter stars.
You mentioned a little bit earlier that we're only seeing some of the planets that are kind of edge onto us. Do we have any information yet from Kepler or anything else about the distribution of how the planets are spinning around the suns? Is it totally random, or are they tending to follow the way the suns go around the plane of the galaxy?
That's a really good question. I think To answer it properly, I'd have to go away and check, but I think everyone at the moment is assuming it's random. In other words, they assume that the solar systems, wherever they are randomly aligned, and they use that to calculate, for example, these fractions that I showed you. If you were to come up and say, actually, solar systems have a tendency to be in the plane of our galaxy, in other words, the stars go around the galaxy and the planets go around, if you were to say that, that would completely screw up all of this, and it would be an amazing discovery. I think the answer is that when you look at the way stars form from gas clouds, they're kind of forming as the clouds clump in, and the way they end up spinning really is a result of the way that the large gas cloud happened to be revolving at the time, because as they collapse, the angular momentum is conserved, they spin up. So it's a little bit like water going down a plug hole. If you have a bath, the water doesn't look like it's moving, but actually it is. You pull the plug out, the water comes in and it ends up spinning one way or the other. Now, there's an old wives' tale that it spins opposite ways in the north and south hemisphere. That's rubbish, right? Cyclones do that, but not bathtubs. The way your bathtub spins is completely determined by what the water was doing when you pulled the plug out, yeah? And it's a 50-50 chance. Now, try it at home, 50-50 chance. Did you? Yeah, the first time I went to the Northern Hemisphere, I actually tried it, and I can't remember which way it went. Now imagine you have a three-dimensional system, so a three-dimensional a ball of gas that's collapsing to become a solar system, and it's got a little bit of rotation one way or the other, and then as it collapses down, that rotation gets amplified, it spins up. And so the theory at the moment, or the assumption at the moment, is that that is random. But it would be an amazing discovery if you could show that solar systems tended to be aligned. But as far as I know, and I'll need to check this, it's an excellent question, we're assuming that they're not aligned.
How do you work out the size and orbital distance of these planets, and why aren't the super Jupiters torn apart by tidal forces?
Okay, so the second question was, why aren't the Jupiters torn apart by tidal forces? So a tidal force is saying that if I am, let's say, close to a star, the tide is the sort of pulling apart of me because my front is closer to the star than my back. So the gravity is stronger at my front than my back. Now that makes for example, the Earth slightly elongated because the moon stretches it, but it doesn't pull it apart. So to be pulled apart by such a thing, you'll have to be very, very close to the star, such that the difference in gravity between the front and the back is huge. And it just turns out that if you put a Jupiter-sized planet close to a star in a 2 or 3 day orbit, the tidal force is not big enough to pull it apart. It probably makes it elongated, but its own gravity is enough to keep it together. They're gas giants. They're not solid, but they're held together by gravity, as indeed is the sun. And gravity works whether you're solid or not. And Jupiter has an enormous amount of mass in it, so its own gravity is strong enough to hold it together and hold it spherical. So that was the first part. The second part of your question was about how we determine temperatures of stars. Yeah, so the size of the orbit is determined by how long it takes to go round, which is easy because it's the time between the transits. But you also need to know the mass of the star, and that's what I'm going to talk about in the second half, how you figure out the properties of the star that's the host.
But you say the orbital distance is quite the period of it, but couldn't it be further out going quicker?
Well, we know the laws of physics, so we know that Kepler's laws tell us that if you have a star with a given mass and you're a certain distance away from it, you then know how fast you go around. That's Kepler's law. It tells you that, for example, if you're 150 million kilometres away from a star that has the mass of our sun, it'll take you a year, 365 days to go around it. The Earth has no choice but to go around the sun in 365 days. If the sun suddenly were bigger or more or less massive, a year would change. But if you replace the sun by another star with the same mass and we stayed at the same distance, that year is fixed. So it's fixed by Kepler's laws, the laws of gravity. One more question, and I will get on to the second half.
Is that why this mission is called Kepler?
Yes, so the reason this mission was called Kepler is because Kepler, the scientist, was really the first one to say that the orbits of planets are ellipses and to write down the laws that describe them. He didn't explain them, that was Newton. So Newton basically came up with the law of gravity that explained the ellipses, but Kepler was obviously instrumental, yeah.
Cool. Yeah, well, my real question is, at the beginning of this mission, it was obvious that there was a lot of gas giants out there and then not so many Earth-like planets. But all of a sudden they are in the minority now. And I just wondered why, if you know why they are so rare, the gas giants.
Why are the gas giants so rare? Yeah, well, I guess it's the formation mechanism. They were the first ones to be found because they're the easiest to find. Yeah. But our solar system may be unusual in having a large gas giant in it. I mean, they're not completely rare. Where's the fraction? You know, a few % of stars have gas giants, but more of them have smaller. So whatever mechanism it is that clumps stuff up to make planets appears to make smaller planets more easily than larger ones. But it's not completely understood at this point. This is still, there's so much data here and remember, these are only a year or two old, these data. Okay, I'm going to push on now with the second half, but we'll pause again at the end. And I'm happy to stay afterwards to answer more questions. I have to get a taxi, I think, at 7:30, but apart from that, I'm here. So the second half of my talk is the research that we do and many others do. We call it asteroseismology, which is Greek for starquakes. So what does this mean? So I'm going to talk a little bit about this, and I'm going to try to tell you three things. One is what causes these oscillations, we call them. Oscillations or pulsations of stars. Now, they've got nothing to do with planets. So I want you to forget about planets for a moment and just think of a star as a big ball of gas, like the sun, held together by gravity. What causes these oscillations, how we measure them, and guess what? We use Kepler, otherwise I wouldn't be doing this. And thirdly, what can we learn from them? What's the science that we can get from them? Okay? So, firstly, what causes their oscillations? So that's easy. The outer part of our sun, and this is just, well, sorry, the left-hand diagram is not what the sun looks like, but I always like to show this cartoon because Gary Larson, I think, was a genius. But the right half of the diagram shows what the sun actually looks like. And the important part here is that in the outer part of the sun, there's a region called the convection zone. And what that means is that the gas moves. You know how hot gas rises because it's less dense. It carries the energy with it, and then it sinks again. That motion is quite vigorous. So it's completely analogous to a pot of water boiling on a stove. Okay, you have a heat source at the bottom, and in the sun, it's the nuclear reactions. The nuclear reactions occur in the core. That's where the hydrogen turns into helium. And that energy makes its way outwards. And for most of the way, it makes its way out through radiation, through light, photons. But in the outer part, for complicated reasons, the star becomes convective. And so the energy makes its way out by the bulk motion of the gas. So here's the pot of water on the stove, and you heat it at the bottom, and you set up this convection, which causes it to bubble. Another analogy is what's called a convection heater, right? You have a heater, the hot air rises, and then it cools, and you get this cycle grown up. Another example is if you take a large room like this, and you put a source at the bottom of hot air like this, then you can get very large convection cells set up. I've given this talk a few times, and every time I give it, I have to change at least one of the pictures at the bottom here. And I wonder how long it'll be before I have to change it again. No politics, no politics. So this is a picture of the surface of the sun taken with the telescope on the ground, and that's a sunspot in the middle. It's about the size of the Earth, so that gives you an idea of the scale. But don't look at the sunspot, look at the stuff around it as I play the movie. It's sped up here. But see that bubbling? So each of those bright spots is the top of a convection cell that's coming to the surface, and then the dark parts are where they cool and fall. And each one of them is probably the size of, I don't know, Victoria or something. They're huge. Okay? But look at the motion. It's quite a vigorous motion, and that motion shakes the star and causes it to oscillate, to vibrate, almost like a musical instrument. Here's another movie, which is a small part of the sun, and this is a particularly vigorous event, which, as you can see, creates what is reasonable to call a sunquake, a starquake. I'll just play it one more time in case you didn't see it. You see that? So that's an extreme example, but I'm talking about the more general example, this shaking of the star. And that shaking of the star causes it to vibrate in what we call oscillations, and that's what we measure. So how do we measure them? Well, there are two ways. This is a movie or an animation showing a star grossly exaggerated, expanding and contracting. But what you have to notice here is that the star is getting bigger and smaller. This is, again, grossly exaggerated, but it's getting a little bit bigger and smaller, which means it's getting a little bit brighter and fainter. And so to measure these oscillations in the way I'm going to talk about today, you need to measure the brightnesses of stars very accurately. Does that ring a bell? So the Kepler spacecraft is perfect for this because it's measuring the brightnesses of hundreds of thousands of stars every half hour, very accurately. So the same data that can be used to find planets, as we've just been talking about, can also be used to measure their oscillations, which is what we do. So here are just a couple of examples. This is the brightnesses of 2 stars observed with Kepler, about a month's worth of data, and the brightnesses are changing by only a few %. But you can see that they're going up and down in these very complicated patterns. There's no planets involved here. This is the star getting a bit smaller and a bit bigger because it's pulsating in a very complicated way. And there's a lot of physics involved in this. If you want to be an astronomer, you have to learn some physics. So what can we learn from these oscillations? Well, I'm only obviously going to touch the tip of the iceberg today. In fact, I gave a seminar to the group here this afternoon where I talked in a lot more detail about this. But one of the simple things you can do is infer how big stars are. So stars come in different sizes, and this is a graph showing 4 different stars. And the real observations with Kepler are these lines here. These are all measurements of the brightnesses of these stars. They're all oscillating. But notice the horizontal axis is different in each case. The bottom one is oscillating a few times every 2 days, so with a period of, I don't know, a few hours. The top one is oscillating a few times every 20 days, a much slower period. So these are stars that are all oscillating, but the bottom one is oscillating much faster than the top one. That tells us that the bottom one is smaller. So just think of musical instruments. You close your eyes and listen to a flute and a bassoon. You can tell which one's bigger. The bigger instrument takes longer for the sound waves to bounce around inside it, and the oscillations are slower. They have a lower frequency. So that's the simplest thing you can do, is you can measure the size of a star. Why do you care about the size of the star? Well, remember this picture. The dip that we were measuring in the first half of the talk was telling us how much of the area was covered. And I said to you, this tells you how big the planet is. But I wasn't telling you the whole story. What it actually tells you is what fraction of the star the planet is. So you don't know if you have a small planet in front of a small star or a big planet in front of a big star. You need to independently measure the size of the star. And this method, measuring the oscillations in the star, tells you the size of the star. So the simplest and one of the most useful things we can do with this method, and this helps to answer some of the questions people were asking before, is to tell you how big stars are, which is something that otherwise is not so easy to measure. And you can do it this way more accurately than you can do it other ways. You can do it to a few %, which is actually pretty impressive for this sort of measurement. So that's one of the things you can do. But it gets more complicated than that. So now we're getting into even a bit more physics. For those of you who've done a bit of physics or engineering, the stellar oscillations I'm talking about are what we call standing sound waves. A standing sound wave is a sound wave inside something with gas. A star is made of gas. It's a big ball of gas held together by gravity. So you could think of these oscillations as sound waves that are going into the star and out again, bouncing in and out. And those sound waves obviously have properties that depend on how fast they travel. So what we can do by measuring the oscillations is we can measure the speed of sound inside a star. Now in this room, sound travels about 300 meters per second, right? It's pretty fast. It's about the third, it's a bit faster than your average aeroplane. An aeroplane, like a jumbo jet, goes a reasonable fraction of the speed of sound. The Concorde went even faster, right? It's pretty fast. But if you go inside a star where it's a lot denser, it travels even faster. What does it depend on? Well, it depends on the temperature of the gas and the pressure of the gas and how big the star is and a whole bunch of stuff and what it's made of. So this piece of information we can get is incredibly valuable. So just to give you a bit of an idea of what we mean by standing sound waves, this is the most physicsy slide in my talk, but it gives me an excuse to play with the demonstration that I brought with me. This is an organ pipe, so a pipe of a musical instrument. And it can oscillate, you see, with sound waves bouncing around inside in several different ways. Its fundamental mode, the lowest frequency mode, or what we call the first overtone and the second overtone. And these are modes where the sound is bouncing around inside in different ways. How many people have seen this sort of thing in physics classes? A few of you. So the good thing is I brought a demonstration so you can hear it. So I have a tube here, right? It's just a hollow, it's a kid's toy. You can buy it from a toy shop. And when you spin it around, it makes a noise. It would also make a noise if I blew over the end, but it's easier to spin it around. But when I spin it at different speeds, the air goes past at different speeds, and I can change from one of these modes to another. And what happens is that the note, the frequency changes. So listen. These are exactly the same modes that are in a bugle. A bugle is a trumpet with no vowels, right? So when you play the last post on a bugle, you're doing this. The only thing you can do is change the shape of the mode. So if you're very skilled, you can play the last post on this, but I'm not. Like that. Now, this is a one-dimensional musical instrument. Now you have to imagine you extend the whole thing into 3 dimensions, because that's what a star is. It's a ball. And when you do that, you end up with something that looks like this. So it's a similar idea that you can have the simplest mode, the fundamental mode. That was the lowest note. Or when you do it harder, you can have the higher notes. A star can do all of these. And that's why the graph I showed you of all the wiggles of the pulsating stars was so complicated, because it's doing all of these at once on top of each other. A very complicated and beautiful musical instrument. Now, of course, we can't hear a star. For one thing, these sound waves are a lot lower frequency. So this sound wave here is a frequency you can hear. It's a few hundred hertz. But the sound frequencies in stars are hundreds of thousands of times lower. So there's no way you can hear them as a note. But the other thing is, of course, there's a vacuum between us and the stars. So what we actually observe is not the sound, but the light. But what happens is, as these sound waves are bouncing around inside the star, they're making it a little bit brighter and fainter, and they're affecting its light output. And that's what we measure with Kepler. But it's even more complicated than that. But anyway, here we go. Stars can oscillate simultaneously in many of these modes. And so that complicated pattern here is the superposition, the sum of all of those modes. And for those of you who are interested in this, and might be engineers or scientists, we use Fourier analysis to extract the information that we want from this. But it's even more complicated than that, because the star is 3-dimensional, and so it can do weird things like this, this, and this. Now, these are only animations, and they're grossly exaggerated, but you get the idea. Right? This tube has only got 1 dimension. There's only one way the sound wave can go. If you have a 3-dimensional star, it can go in all different directions, and we can get what are called non-radial modes, modes that don't go along a radius, but go in all different directions. Okay? And so that's what happens in real stars. And so we get all of these modes on top of each other. Incredibly complicated. But each one of them has its own oscillation frequency, which we can measure. So what can we do with all this? Well, the main thing we can do is test the laws of physics under very extreme conditions. We can measure the speed of sound in a gas that we can't reproduce on Earth. The interiors of stars are much hotter and have much, much higher pressure than any laboratory. And so we can test the laws of physics and improve our understanding of how stars work. And indeed, there are groups at this university who are doing exactly that as well. So I have an oscillation of the sun sped up to make it audible to you. So these are the actual oscillations of the sun. I'm about to play you an audio tape, sped up by 300,000 times so that they come into the audible range. So this is the music of the stars. So it's unlikely to make the top 100 of songs, but that is quite literally the music of the stars that indeed Kepler himself was interested in at the time. It's the actual oscillations of the sun sped up so that they're into the audible range. So there's an awful lot of stuff you can do with this. I'm only going to mention one more, which is that we can measure the ages of stars. And this is particularly important because ages of stars is otherwise almost impossible to measure. And it's interesting, right? If I find a solar system out there with planets, it would be interesting to know how old it is. And just recently, a few months ago, we published a paper which got a lot of attention because we found a system with planets from Kepler. And the star it was going around was more than twice as old as our own sun. It was something like 11 billion years old. Our sun is only 4.5 billion. Okay? So that's a reasonable fraction of the age of the universe. The universe is only 13 billion years old. We had a star 11.5 billion years old. How do we measure its age? The answer is that as the star gets older, the nuclear reactions in the middle that are turning hydrogen into helium in the center, yeah, because that's the fusion reactions, change the speed of sound. So the speed of sound which we're measuring throughout the star varies in the centre very gradually over billions of years because hydrogen is being converted into helium. And this is the point where if I'd had a helium balloon, I would breathe it and make my voice go funny. Unfortunately, wasn't able to bring one with me on the aeroplane. But you all know the party trick, right? You breathe helium and it changes your voice. The reason it does that is the speed of sound is different in helium than it is in normal air. So the effect in stars is that as they get older, the speed of sound inside changes, and we can use that to measure their ages. And we were able to do that for this particular star and show, as I said, that it's nearly as old as the whole galaxy, which shows you that planets have been forming from the beginning. So they're not a new phenomenon. We know our Earth is only 4.5 billion years old. This is a star 11.5 billion years old that has planets around it. So whatever alien life form is on those planets has either long since blown itself up or killed itself with global warming, or maybe it's still there and going to colonizing the galaxy as we speak. Okay, so that brings me to the end. I'm going to leave you with my final slide just to show that I'm not just a scientist but also like a bit of Shakespeare. The reason I like this quote, there are more things in heaven and earth than are dreamt of in your philosophy, is that as we look out there and find these solar systems and these stars, they're weirder than we ever imagined. There is no need to posit anything supernatural to get excited about the world. The natural world, the world of the universe that as we explore it, is more than enough to satisfy our curiosity and our thirst for new and exciting things. So thank you very much for your attention tonight.
Thank you very much, Tim, for your talk. And any questions? We have James with the microphone coming down.
Could we go back to the slide where you showed how you measure the size of the stars?
That one?
Yeah, that one. It strikes me that if you were measuring the size of a blue giant as opposed to a red giant, you might get different oscillations and different information altogether.
Yeah, so that's a very good point. Blue giants oscillate differently to red giants. So I've simplified this thing enormously. I guess one answer to this is it turns out that blue giants are not very common. Most of the giant stars are actually red giants, cooler stars. But an extra piece of information we feed into this when we calculate how big stars are is their temperature. And indeed, I talked about this in my seminar this afternoon. So if you want to know how big a star is, you need to know if it's blue or red, in other words, how hot it is, as well as knowing what its oscillations are doing. And those two pieces of information together give you the size of the star. Yeah, so I guess I did gloss over that a bit. What is the period of any of those? I guess the simple answer is that while there's no... Let me go to a one that's a little bit nicer looking. That one. So while that's clearly not exactly regular, it kind of has a typical period. I mean, this scale here is in days, so it goes for about a month. So this star, I would say, is probably oscillating with a period of about 1 day. Okay? If you want to measure it more precisely, you do something called Fourier analysis, which takes a complicated signal like that, does a Fourier transform mathematically, and that allows you to measure what the periods are. And the point is that there's more than one in this star. It's not oscillating with a single period. And it's like this thing here is oscillating with many notes at the same time. Imagine adding them all together. So in fact, the information is far richer than I've said. It's not just a single period. There's a whole bunch of them. And in fact, all of those periods together give you a lot more information. And comparing those with theoretical calculations is what gives us the sizes of the stars.
How do you differentiate oscillations from transits?
So oscillations and transits look very different. Clearly that has a very different shape from that. So one of the things is the shape of the light curve. Another is the time scale. So this thing will reoccur every few days or weeks or months, whereas an oscillation will go on continuously with its typical period, which might be hours or days, forever. So they do look very different. There's occasionally cases where there is some confusion, but most of the time it's pretty easy to tell the difference.
The periods
The periods can be similar. So the sun, it depends on the size of the star. The sun's oscillations actually are much shorter. The sun has oscillations with periods of only minutes, 5-6 minutes, something like that. So red giant stars, which are the ones I showed you in that picture we were just looking at, have periods much longer. They have periods of, oh, I've gone the wrong way. They have periods of days. So it really depends on the size of the star. These stars here, apart from the sun at the bottom, which isn't shown, have much longer periods.
Two related ones. Do we have the data or the sensitivity to detect the equivalent of solar flares and or the sunspot, 13-year cycle that we have with our star?
Yeah, so that's a good question. Solar flares, the answer is yes. Kepler sees many stars that have flare-like activity. And the reason it can do it is many stars have much stronger flares than the sun does. If you were to observe the sun or a solar twin with Kepler, I should be a bit careful here, but I don't think you would notice the flares. The flares that the sun has, while we might think they're important, because occasionally they interfere with our communication, are actually pretty weak. But there are stars out there whose flares are much, much stronger. And sorry, what was the second question?
It's around the solar cycle.
Oh, the solar cycle. So the sun has an 11-year cycle of magnetic field changes where the sunspots increase in number and go away again every 11 years. And that's to do with the way the magnetic field in the sun gets stronger and weaker over time and indeed changes direction. Other stars also do that, and it affects the frequencies of the oscillations. And indeed, we see that in the sun. The oscillation frequencies of the sun change ever so slightly over an 11-year cycle. And there's some evidence so far that other stars do it. But clearly 11 years is a long time, and Kepler hasn't been observing that long. But fortunately, there are some stars that have shorter magnetic cycles, and there are a few at least where it seems like in only a couple of years their magnetic fields get stronger and weaker. Magnetic fields is a very complicated piece of physics to understand in stars.
I still have one question. We live in the southern hemisphere, and you showed the Southern Cross. And I live here since 1984 in North Springvale, and the Southern Cross was closer to the horizon. Now it's a little bit higher. What happened? It's like observation wrong?
No, you are just looking at a different time of night or year. So if you look over one night, that whole pattern rotates in 24 hours. Okay, so the Earth's axis is pointing to a point that's about here, where my red spot is, off the bottom of the screen. And in 24 hours, this whole pattern rotates around this spot in a big circle. And if you take a long exposure image of the night sky, you see these stars going in circles. But it depends also on the time of year. So if you come back 6 months later, at the same time of night, it'll be down here. So some of the time the Southern Cross is below the horizon. But from where we live, most of the time it's above the horizon. Okay? So all you have to do is go look at the Southern Cross and go out an hour later and you'll see it's moved. Yeah.
What is actually driving the oscillation?
Just 1 second till the microphone comes, please.
What is the energy source driving the oscillations? Is it an impulse response to something that went bang, or is there a positive feedback establishing an oscillation?
That's a terrific question. So in the sun, it's a continuous driving from convection that's driving the oscillation. So it's a type of noise source. We call it acoustic noise from the convection, the bubbling of the pot on the stove, continually shaking and shaking and shaking. But there are some stars, one example is called Cepheid variables, which you might have heard of, where there's a feedback mechanism, where the source of the oscillations is a repetitive feedback heat engine mechanism. But in all cases, the ultimate source of the energy is the same as the energy source of the star itself. It's the nuclear reactions in the middle. The nuclear reactions are the source of the oscillations. They're the source of life on Earth. Almost every energy source we have comes from the sun. The only exception that I can think of quickly is nuclear energy, which comes, say, from the uranium that we dig out of the ground, which is radioactive. But apart from that, all the energy that we have available to us and the sun has available to it comes from the nuclear reactions in the center of the sun.
Albert Einstein was quoted as saying, the more we learn, the more we realise how much we don't know. I guess you'd agree with that.
I certainly would. There's another quote I've heard, I don't know if it was Newton, who said, the larger the island of knowledge, the longer the shoreline of wonder, which I particularly like as well. We make progress all the time. We learn more and more and more. And if I look back even on my own career, it's amazing how much we know that we didn't. But there's so much more out there to be discovered. It's just extraordinary, yeah.
Thank you. Getting back to your first topic of the lecture, before Kepler, the first tentative discoveries of planets was from gravitational microlensing. Has there been any progress in that field?
Yeah, so microlensing is one of the methods that has been used and is still going on. People are still using it to look for planets. This is what happens when a star that has a planet in front of it happens to pass in front of a distant star. And the gravity from the nearby system, for a small time, only a few days, makes the distant star brighter. And that brightening is a gravitational lensing effect predicted by Einstein general relativity. It requires a lot more coincidences than this method, and so it hasn't been used to find as many planets, but it has. The other method that's found most planets before Kepler was the Doppler shift method, which is to measure the shift of a star as it's pulled by its planet. A planet goes around a star, the star wobbles a little bit. You measure the Doppler shift of the star very accurately from ground-based telescopes, and that was the method that found most planets before Kepler. They're all complementary methods. They find different planets. They have different strengths and weaknesses. Up the back, yep.
Firstly, thank you for an amazing and inspiring talk. Secondly, because Kepler and I think similar telescopes have only been around for a few years, how do we detect planets that are that have an orbital radius like Jupiter? And is there like a big lack of information about them?
The short answer is yes. There's clearly a bias towards the shorter period planets. But the velocity searches I mentioned, the Doppler shift searches, have been going on for decades now. The very first confirmed planets were discovered in the mid-90s around other stars by the Doppler method, and they were hot Jupiters. But the cool Jupiters, if you like, the real Jupiters with 12-year periods, some of those are known now. I'd have to check, I can't remember the numbers, but there are certainly some planets known from the velocity method, the Doppler shift method, with longer periods. Kepler itself has stopped observing the main field after 4 years and is now observing other fields in other directions. So it will never find a 12-year planet. There are missions coming up. There's an American mission called TESS, which is scheduled to launch in a few years. And that will cover the whole sky, but some of it will at least be staring. And if that works for a long time, may find longer period planets. But longer period planets are definitely harder to find. There's no doubt about it. Any more questions? So okay. I was going to say I'm happy to hang around for another 20 minutes, 15 minutes. But
I've got two questions.
Want to go, I guess.
My first question is, how far away are these stars that you've discovered planets around?
How far they are away? Well, I guess this picture, maybe you can't read it, but the furthest stars on that picture are about 3,000 light years, but most of the stars that we look at are a lot closer than that. We can only do astroseismology on the nearest brightest stars. So we're talking about a few tens to 100 light years, something like that.
My second question is going to be, as light takes so long to reach us, is it possible that you've discovered planets around stars that don't exist?
Well, I guess anything's possible, but 3,000 years is not very long, right? Yes, of course, every time you look out in space, you're looking back in time. But even if you look to the center, across the entire galaxy, you're not looking back very long in astronomical timescales. I mean, the sun itself, if you come back in 1 million years, will look more or less the same as it does now. Whether we'll be here or not is a different question, of course. There are planets thought to be around Alpha Centauri B, which is the B component of the triple system, but they're disputed. So there's a claim from velocity from the ground about planets around the Alpha Centauri B star, and there was a paper just the other day about that, which I noticed, but I haven't got around to reading yet. But it's controversial. So the answer is maybe. Of course, it's interesting because it's our nearest system. It's the one they were going to in Lost in Space. Did anyone watch Lost in Space as a kid? Amazingly, they never got there, but they found lots of other planets on the way, which is a bit weird. But
Yeah, hi. Just two questions. Firstly, has that Doppler method and this Kepler method, have they complemented each other with the discoveries of planets?
They're complementary in the sense that the Doppler method allows you to measure the mass of the planet. So the Kepler method only allows you to measure its size, but it doesn't tell you how much it weighs. So it doesn't tell you its density. If you can, at the same time, measure the Doppler shift of the star, you can get the mass as well. And that's what allows you to tell the difference between, say, a rocky planet and a bigger planet that's made of gas or water. So absolutely, they're completely complementary, yes.
Yeah, great. And then the last question, could this be a method with which we could plan to visit exosolar planets in the future?
Well, the problem is the distance. I think, did anyone watch Q&A? Brian Schmidt was on Q&A last night, and someone asked him how long it would take to get to a particular new discovery. It's tens of thousands of years, even if even with modern technology at least.
To change that.
It's unless someone finds a wormhole, like in that movie Interstellar, which is a great movie, I have to say, although perhaps implausible, but at least not. It was the scientific advisor on the movie Interstellar. Kip Thorne is a real physicist. Like, he's famous for writing books on general relativity. But still, going through a wormhole to travel great distances and surviving that is a pretty big long shot, I think. Even communicating. You want to communicate with someone where you have to wait 20 years to get an answer? It's kind of boring, but... Okay.
We'll wrap it up there. Tim will hang around for another 5 minutes if you want to ask him some questions. We have a little gift from the Monash Centre for Astrophysics. Thank you for coming and giving us this great public talk.
Thank you very much.